Hi everyone, my name is George Adamson. I'm a senior at the University of Michigan studying aerospace engineering, and today I'm going to present my honors capstone, which is the optimization of the LAX to JFK flight route to minimize population exposure to sonic booms. To begin, I'm going to provide some relevant background information. My project revolves around supersonic aircraft, and the most famous example of that would have to be Concorde, which could fly between New York and London in about 3.5 hours. And it flew in the late 1900s before being retired in 2003. Now, Concorde was limited to flying over the ocean because it produced something called sonic booms, like any supersonic aircraft does. And these sonic booms are very similar to thunder in that they're loud and can startle people, but they're even a little bit worse in that they can cause vibrations as well as the potential to produce structural damage. There have been cases of windows and glass actually breaking from these sonic booms. These sonic booms were so disruptive that the FAA, or Federal Aviation Administration, actually decided to ban supersonic aircraft from flying over the United States. And this ban only applied to commercial supersonic aircraft, and it's still in effect today. So now moving into my project, I basically wanted to answer a hypothetical question. So if the Concorde were to fly over land between Los Angeles and New York City, could its flight route be optimized such that the number of people disturbed by sonic booms is minimized? Now, with any optimization problem, you have to start by defining some baseline metrics, otherwise you don't have anything to compare your optimal results against. So I have two baseline metrics, one for flight time, and then the other is for the number of people disturbed by sonic booms. Now these are best described in this table below, so you can see I have two parameters I can change, the aircraft flying the route and then the route itself. For a subsonic aircraft I decided to use a Boeing 767, and then of course I'm using Concorde as the supersonic aircraft. And then the route is either a typical route in use today for the baselines, and then an optimized route of course for the optimal results. So why is this project important? Well, supersonic aircraft have the ability to reduce flight time significantly, which could obviously benefit both passengers and cargo companies. And it's already been shown that these commercial supersonic aircraft are feasible, it's just that their deployment has been limited to oceanic routes. So there needs to be some research investigating how these aircraft could possibly be deployed over countries like the United States. I'll now go into how I define my baseline. So I use the flightaware.com website, and this has a unique feature in that it can tell you the most common routes being flown in any 2-week period. So you can see in this figure below, this might be a route that you could fly tomorrow if you got on an aircraft between LAX and JFK. For the optimization side of things, I decided to summarize the process in a flowchart here. So I start with two data sources, population data and waypoint data. I condense these into something called a cost matrix, and then I use Dijkstra's algorithm to actually solve the cost matrix and output an optimized route. So for data sources, I primarily used government agencies like the US Census Bureau here in the US, but I also had to get population data for some of the neighboring countries like Canada, Mexico, Cuba, and the Bahamas. This is because the aircraft can sometimes fly near these countries or even over them in some cases. I also needed waypoint data. And waypoints are just intermediate points that help guide the aircraft between the two airports. And here in the US, our waypoints primarily use GPS, so you have a latitude, a longitude, and a 5-character name for every GPS waypoint. And you can see they're distributed well across the country, and there are upwards of, I think, 70,000 just here in the US. Using these two data sets, I can then estimate the cost of flying between any two waypoints in the data set. So to do this, I define two waypoints, I put them on the midpoint of a rectangle, and this rectangle approximates the region in which people on the ground might hear sonic booms, and it's called the primary carpet. I can then use a Python script to count the number of people that live in this rectangle, and that's basically the cost of flying between any two waypoints. Now I have to do this for every waypoint in the dataset, and this can be pretty expensive. It's an n-squared problem. To simplify this, I use something called distant neighbors, which I won't go into the details here, but it basically reduces the computational expense from n squared to k by n, where k is much smaller than n. So here's an example of what the cost matrix looks like, and you can see, for instance, if you want to fly between waypoint 1 and waypoint 2, the matrix tells you that approximately 104,000 people will hear sonic booms. You can also see that this matrix is sparse, and that's because I was using the distant neighbors simplification. I can then solve this cost matrix using Dijkstra's algorithm, and this algorithm is very good at finding things like geographic features where nobody lives. So in this figure here, this is the Great Salt Lake in Utah, and you can see that the algorithm knows that nobody lives over the Great Salt Lake, so of course it would be a great place to actually fly a supersonic aircraft. So that kind of concludes the optimization process. I'll now go into presenting some of my results. So the subsonic baseline, again, is what aviation looks like today. And the flight time does not include things like taxi, takeoff, or landing, so it is on the shorter side. But you might think that at cruise, a typical flight today would take about 4.5 hours. And because this is subsonic, 0 people would be exposed to sonic booms. The supersonic baseline, again, uses the same route, but we've just swapped out the subsonic aircraft for a supersonic one, Concorde. And the flight time drops to 1 hour and 53 minutes, which is very good, but 43 million people are exposed to sonic booms, which is very high. You can try to reduce that figure a little bit by adding some speed restrictions over the LA and New York metropolitan areas. That increases the flight time slightly, but it decreases the population impaction very much to 13 million people. But that is still a very high figure, so optimization is needed. So the first optimal route I'll present is this one, and it has a flight time of 3.5 hours, so it is about an hour shorter than the subsonic baseline, and approximately 250,000 people are exposed to sonic booms. With some post-processing, you can actually reduce the flight time by about 15 minutes to 3 hours and 20 minutes by just crossing Florida subsonically, and the population impaction stays the same. As an honorable mention, this route is a middle ground. It has a slightly shorter flight time of 2 hours and 49 minutes, but slightly more people are exposed to sonic booms, upwards of about 800,000. So these results are then presented in a table here, and you can compare some of the various metrics for the baselines and optimal routes. You can also look at this in a more mathematical way by plotting the population impaction and the flight time. And this actually shows that an asymptote will appear, and this asymptote is actually pretty trivial. It basically tells you that at some point, instead of deviating around population centers, you'll be flying as directly as possible between the two airports. And in this case, it's impossible to reduce the flight time any further. So in conclusion, for one, aircraft routes can definitely be optimized on the basis of the number of people exposed to sonic booms. And these optimized routes still achieve flight times that are shorter than their subsonic counterparts. And this is pretty impressive because a lot of these optimized routes are very elongated because they have to fly around population centers. However, there are still some hurdles to overcome, the major one being that approximately 250,000 people are exposed to sonic booms in the most optimal case. And that's a figure which is unlikely to change any minds at the FAA. For future recommendations, I think some more rigorous optimization techniques would go a long way, as well as using a more complex sonic boom model that does not assume cruise conditions for the entire flight. And in my opinion, to solve this problem, it's likely going to take a joint effort between researchers quieting the sonic boom itself and those optimizing aircraft routes. I'd like to acknowledge Professor Amy Cohn, who is my Capstone advisor, as well as Rachel Armstrong-Cerrone, the honors advisor, as well as my uncle John Pendleton, who is a captain for Delta Airlines. They all provide some great support over this capstone. Thank you for your attention. I'd be happy to answer any questions if you leave them in the comments below.